If we wish to use texturing, here we show how to upload an image to the GPU that is to be used as a 2D texture. A texture is a resource, so first a resource ID should be generated similarly to VAOs and VBOs. Texture IDs are generated with the GL generate textures function. The first parameter, similarly to VAOs or VBOs, is the number of IDs to be generated, and the second is an array where IDs are given back. Now we generate just a single ID, so the array has just a single element or can be unsigned int. We bind the generated texture ID to the rendered target, which is a two-dimensional texture called GL texture 2D. It means that from this point, all operations that use a GL texture 2D resource will refer to this texture until another ID is bound. With the GL text image 2D, we can upload the image to the texture. The parameters are as follows. The GL texture 2D is the target, so this operation will modify that texture which is bound to the GL texture 2D resource, which is all texture that was generated here. The next parameter is the current mipmap level, 0 in this case. Then we describe the target format, which is RGBA. So this is a color texture where alpha values are also stored, so this texture can represent transparent colors as well. Width and height define the resolution of the texture. The border is currently 0. This border parameter may add extra pixels at the boundary to support, for example, bilinear filtering even at the edge of the texture. The next parameter is the source format, which is RGBA again, and all of them are interpreted in floats. Finally, we should define the starting address in the CPU memory from which this copying operation will be executed. Additionally, texture sampling and filtering is also specified using the GL text parameter function. Here we use the nearest neighbor filtering or no filtering for the minification case and bilinear filtering for the magnification case. Note that OpenGL is an output library, so it gives no help to create or read a texture from a file. So the preparation of this image array is the programmer's responsibility. The second step of texturing equips the object to be textured with texture coordinates, or also called UVs. That is, for every vertex we also specify a texture space point from where the color or data should be fetched if this vertex is rendered. If in the shown program or VAO has two vertex buffer objects, one stores the modeling space Cartesian coordinates of the vertices and the second the texture space coordinates of the same vertices. The filling up of the texture coordinates are shown here. We direct modeling space coordinates to input register number 0 and texture space coordinates to input register number 1. When the object is rendered, the content of the VBOs flows to the vertex shader. The vertex shader gets the location of the vertex in input register number 0. We call this input register as VTX position. It directs the UVs or texture coordinates to input register number 1, which is called VTX UV in the vertex shader program. The location is transformed to normalized device space and written into the GL position output register. The input texture coordinate is called VTX UV is copied to the output register called text chord. The fixed function hardware interpolates the texture coordinates and generates a sequence of pixels for which the fragment shader is run. The fragment shader looks up the texture memory using the interpolated texture coordinates called text chord. The fragment shader looks up the texture via a sampler unit identified by uniform variable called sample unit. The texture function then returns the filter texel value, which is assigned to the output variable called fragment color. When an object is rendered, we should select the active texture and also connect the shader processor to this texture via a sampler unit. The sampler unit variable of the shader program gets the ID of the sampler unit, which is 0 in this particular example. This number can go from 0 up to the number of sample units available in our GPU, and this is at least 8, but typically much higher. With the GL active texture function and with the GL bind texture, we can establish a connection between the texture memory and the sampler unit on the other side of the sampler unit. Finally, we can send our object identified by the VAO through the pipeline and enjoy its textured rendering. An image needs to be shown on screen. We can do it by rendering a full viewport rectangle textured with the image. On the CPU, a rectangle is defined by an appropriate coordinate system, which is preferred to be the normalized device space since vertices have to be transformed to normalized device space anyway. So this is on the CPU side. The vertex shader gets the vertex in normalized device space, which is just copied to the GL position output register without any relevant modification. Additionally, the texture coordinate called UV is also calculated. In normalized device space, the full viewport rectangle has opposite corners -1, -1 and +1, +1, while in texture space, these opposite corners are 0, 0 and 1, 1. So UV is computed by mapping the two different coordinates. When the rectangle is rasterized, the UV texture coordinate is interpolated for internal pixels. So when the fragment shader runs, its input parameter UV refers to the texel corresponding to this particular pixel. Texturing is just done by looking up the texture with the interpolated texture coordinates. Note that the sampler unit, called texture unit, will perform bilinear or mip-map filtering if it is configured accordingly. In the previous example, the texture was looked up at the location determined by simple interpolation. If we apply a distortion in adverse calculation, we can distort the image itself. For example, if the texture is looked up at a location U star, which is for example U plus 0.1, then the interpolated U is increased by 0.1, then the new image will be translated. We are not restricted to simple linear operations, which opens room for very many exciting image effects. So let UVC a point in texture space, which is selected by the current cursor. The texture coordinates are modified in the center of radius R around UVC. Well, in this program we specify the square of the radius directly. The modification is just a simple cubic function, which has the effect that a magic lens magnifies the image around the cursor. Swirl is a rotation where the angle of rotation gets larger as we approach the center of rotation. The rotation angle, ang, is controlled by an exponential function of the distance between the current pixel UV and the cursor position UVC. The rotation is executed around the UVC here, first translating the UVC to the origin, rotating by matrix rotmat around the origin, and finally translating the origin back to UVC. In this black hole effect, we assume that a large mass but small size object, for example a black hole, is in front of the image, which distorts space and also lines of sight. The amount of distortion can be computed exploiting the equivalence principle that states that gravity and acceleration are the same and cannot be distinguished. So we can easily determine the amount of light bending when our room is accelerating in a direction. Then the same formula is applied when the room stands still but a black hole distorts the space. In this final demo, we assume that image is covered by water and its surface is distorted by a wave started in a single point and moving in all directions with speed c. The width of the wave is wave width, its amplitude is decreased with the travel distance. The distortion is computed by applying the Snell's refraction law on the water surface. Let me have a short demonstration. First, the lens effect. The lens follows the cursor movement and magnifies one part of the image. The second was the swirl. The center of the swirl is just the cursor position. This black hole effect distorts the space in a physically plausible way, as real black holes would distort the space. And finally, the wave is started by the cursor position. When clicking happens, and I can start a new wave from any point.